we've seen that ethanoic acid is an example of a weak acid, and we are going to compare now the reactions of ethanoic acid, which is a typical carboxylic acid, with the reactions of a strong acid, hydrochloric acid. So to do this, first of all, I'm going to put into my beaker approximately equal amounts of ethanoic acid into one beaker and hydrochloric acid into another beaker. And I'm going to start by measuring the pH of this solution using a pH meter. And my pH meter is stored in a solution which has a pH of exactly 6 to keep it calibrated. So I'm going to remove the sensor from the solution and I'm going to rinse it with distilled water to remove any of that solution which is still on the pH sensor so that it's ready for use. Okay, so the first thing I'm going to do is I'm going to test the pH of my hydrochloric acid. I'm going to place my pH sensor in my beaker and I'm going to monitor the pH on the computer, and we can see that the pH of that solution is 1.35, which obviously means that the hydrochloric acid is very acidic, which is what we should expect from a strong acid. Okay, now I am going to rinse my pH meter again, just to remove any extra hydrochloric acid which is on there. And then I'm going to do the same thing. I'm going to put it into my ethanoic acid. Wait for a second, and then I'm going to look at the pH of that solution. Okay, and we can see that the pH of that solution, it's still going up slightly. Okay, so it's around pH 3.1, 3.2, which means it's still acidic, as we would expect from the name ethanoic acid, but it isn't as acidic as the hydrochloric acid. This is because pH is a measure of the number of hydrogen ions in the solution. Hydrochloric acid, as a strong acid, is going to have more hydrogen ions than ethanoic acid, which is a weak acid. So that's the first thing I'm going to do, is I've tested the pH of those solutions using a pH meter. If I didn't have access to a pH meter, then I could use universal indicator solution. And I should again find that there is a difference in the acids. Okay, so they are both turning red, because they're both acidic. Okay, we should be able to see, however, that the red on the left is a slightly more orange red, showing that it's a weaker acid, whereas on the right, it's a stronger red, which shows that it's a stronger acid. We can also look at the reactions of these acids with other substances. Okay, so the first test that I'm going to do is I am going to react both of my acids with magnesium ribbon. Okay, so I'm going to start with hydrochloric acid and then ethanoic. Approximately equal volumes of acid, and I'm going to add a piece of magnesium ribbon to each one. Okay, so again, we can see that they are both fizzing. Okay, they're both effervescing. Okay. And we can see that the number of bubbles produced in both cases is quite high. Okay, we're going to wait and see if we can see a difference in those two reactions and how quick they are. While I'm waiting for my magnesium to react, I'm going to set up my second experiment. So again, on the left-hand side, I've got my hydrochloric acid. Hydrochloric acid is on the left in both reactions. And on the right, I've got my ethanoic. Again, try and make sure that the amounts in there are approximately equal. Okay, and the second reaction that I'm going to do is I'm going to add sodium carbonate powder to each of these substances. And what you should see with sodium carbonate powder is that carbon dioxide gas is produced, and carbon dioxide gas will be released as bubbles. Add a small spatula of sodium carbonate to each. Okay, so again, you can see that they both fizz when you add your sodium carbonate to them. Okay, and we're looking again at the amount of solid that's left in both cases. Okay, so we can see that the reaction with the hydrochloric acid is finished. Okay, whereas the ethanoic acid one is still producing bubbles because there is still some carbonate left in that tube. Okay, more carbonate is left there, whereas in the hydrochloric acid case, it's pretty much entirely reacted. Okay, whereas the other one here is still fizzing up. Okay, so that shows that the reaction with the carbonates is much slower with ethanoic acid than it is with hydrochloric acid. The hydrochloric acid has completely reacted with the sodium carbonate. Sodium carbonate is all gone in the one on the left, whereas in the one on the right, it's still fizzing. Okay, the reaction with the magnesium is still going. Okay, I'll come back to that one, restart the video when one of them disappears. Just coming back to my results with the universal indicator, I've put them both against a white background just because I didn't think the colour difference was very clear in the previous part of the video. Okay, so you hopefully now can see we've got the hydrochloric acid on the right and the ethanoic acid on the left. Hopefully now it's a little bit clearer that the one on the right is a redder shade of red, whereas the one on the left is slightly more orange because it's weaker. Okay, the reaction of the magnesium with the hydrochloric acid is now finished. Okay, so you can see that there is no more magnesium in the tube which contained the hydrochloric acid, whereas the one in the ethanoic acid still got quite a large piece of magnesium there. Okay, so this shows that our hydrochloric acid was the stronger acid, okay, and it has therefore reacted with the magnesium more quickly. Okay. You would also expect the reaction with the hydrochloric acid to produce more bubbles than the one with the ethanoic acid. So at the beginning of the reaction, We saw quite a lot of bubbles from both of them, but we should see more bubbles at the beginning from the hydrochloric acid than the ethanoic acid, because the hydrochloric acid is stronger. Obviously now the reaction in the hydrochloric acid is finished, which is why the ethanoic acid still has more bubbles in this case. Okay, looking at the reactions which are taking place, okay, they're following the same patterns with the carboxylic acids as they do with a normal acid-metal reaction. So we know that when we add an acid to a metal, we get salt and we get hydrogen. And we've seen previously that reactions with hydrochloric acid produce chloride salts. For example, hydrochloric acid plus magnesium makes magnesium chloride and hydrogen. We found that sulfuric acid produces sulfate salts. Another example there, this time sulfuric acid and magnesium makes magnesium sulfate and hydrogen. The carboxylic acids produce salts with different endings. So if you start with methanoic acid, you will get a methanoate salt. If you start with ethanoic acid, you will get an ethanoate salt. And if you start with propanoic acid, you will get a propanoate salt. Okay? In each case, hydrogen is made. In the symbol equations, you can see that I have underlined one of the hydrogens in both the methanoic acid and the propanoic acid. Okay? That hydrogen is the one that is being replaced. So what's happening in this reaction is that a hydrogen atom is leaving the acid and being replaced by the magnesium. Okay. Those hydrogens are then going to pair up to form hydrogen gas, which is why I need two of everything else. So I'm going to have two methanoic acids, each of which is going to lose that underlined hydrogen. The underlined hydrogen will be replaced by a magnesium, and the two hydrogens that have been removed are going to pair up to become the H2 gas at the end.